Welcome back to AI Paper Podcasts, where we like to take apart the most interesting new AI research. Today, we're going deep on a paper that I think will resonate with a lot of you out there. It's about this huge models, specifically mixture of experts models, or MoEs, as we all know them.
Oh yeah, those MoEs, they're amazing for scaling, but they can be real memory hogs when you're trying to actually use them.
That's it. And that's exactly where this paper, eMoE, task-aware, memory-efficient mixture of experts-based MoE model inference, jumps in. They've come up with some really clever ways to optimize MoE inference, and the best part is they don't sacrifice accuracy in the process.
And for all of you who really need to stay at the cutting edge of this stuff, we'll give you the big takeaways right up front.
All right, so in a nutshell, what have these researchers discovered?
Well, they found that the way experts are chosen inside these models isn't totally random. There are actual patterns. And once you see those patterns, you can start to optimize things in a really smart way.
So there's like an underlying structure to how those experts are selected.
You got it. And that's huge because it means we can actually predict which experts we're going to need ahead of time. So instead of constantly loading and unloading them, which is super slow, you can preload the ones you're likely to use.
That makes a lot of sense for speed. But what about memory?
Well, they've cracked that too.
Yeah.
They've shown that not every task needs the absolute perfect expert all the time.
Oh, interesting. So some tasks are more forgiving if they don't get the top expert every single time.
Yeah, exactly. They actually call it routing inaccuracy. Basically, it means not always hitting that perfect expert match.
But they can still get great results without it.
Exactly. And they even visualize this in the paper. You can actually see how certain tasks like classification hold up really well, even with a little bit of routing noise.
So like some tasks are okay with a generalist while others absolutely need the specialist.
Perfect analogy. And that's a key insight because eMoE uses this to its advantage. It makes sure the tasks that are really sensitive to needing the exact right expert get it.
While the more flexible ones can maybe make do with a slightly less perfect match.
Precisely. It's all about finding that balance between getting the right answer and using resources efficiently.
And that's where eMoE shines, right?
Absolutely. They managed to get some incredible results, like a 17% reduction in latency, which is huge when you're talking about real-time applications. And they slashed memory usage by up to 80%.
Wow, 80%. That's not just an improvement, that's like a whole new playing field.
And the best part is, they did all of this without sacrificing the accuracy that we expect from these powerful models.
All right, now I'm really intrigued. Let's dive into the nitty-gritty of the paper and see how they pulled this off. The paper starts by talking about this huge memory and latency problem inherent to using MoE models, right?
Yeah. They lay out the challenge really clearly in the beginning. LLMs, especially when you're using these mixture of experts, they just eat up memory during inference, way more than your typical dense models.
And how much more are we talking?
Well, according to their analysis, it can be anywhere from 4 to 14 times more memory consumption. And if you've ever worked with these large models, that's a big deal, especially if you're trying to deploy them in real-world scenarios.
Totally. So I guess the obvious question is, why not just dynamically load the experts as you need them?
Right.
Like, only call in the specialist when you absolutely need their expertise.
Right. It sounds so simple, but in reality, it creates a whole other set of problems.
What do you mean?
Well, as the paper points out, this dynamic loading introduces a massive amount of latency. They actually saw inference times slow down by up to 5 times in their tests.
Ouch. So it sounds like that seemingly elegant solution just backfires spectacularly.
Pretty much.
Sure.
The bottleneck becomes the time it takes to transfer those experts back and forth between the CPU and the GPU, and that overhead just completely outweighs any benefits you might get from dynamic loading.
All right, so that idea is out the window, but what about existing approaches? I know the paper mentions a few, like pre-gated MoE, MoE Infinity, and Edge MoE.
Yeah, those are all good attempts to solve this problem, and they each have their own strengths. But they also have limitations. Pre-gated MoE is faster, but it adds a lot of complexity and requires retraining the entire model.
And that can be a real pain, especially with these massive models.
Exactly. And then you have MoE Infinity and Edge MoE. They're interesting, but they might not be the best fit for those really huge models that are becoming more and more common.
So none of them quite nail that perfect combination of simplicity, efficiency, and scalability that we're all looking for.
You got it. And that's where eMoE comes in with a fresh perspective.
And this is where the story gets really exciting, right? Because eMoE doesn't just try to tweak existing solutions, it goes deeper. It leverages these fundamental observations about how MoE models actually behave during inference.
Exactly. The first big observation is that there are repeating patterns in how experts are selected.
So it's not totally random like we might have assumed.
Nope, not at all. The paper shows this beautifully in figures 3, 7, and 8. They show how predictable expert selection can be, both within the different layers of a model and even between different prompts.
So we can actually predict which experts are going to be needed.
Precisely. And that opens up a whole world of possibilities for optimization.
Because we can preload those experts onto the GPU and avoid that super slow dynamic loading process.
Bingo. That's how eMoE tackles that latency problem right out of the gate.
Clever. But it's not just about predicting which experts we need, right? It's also about knowing when to actually make those predictions.
You're absolutely right. Calling that predictor for every single request would still add way too much overhead.
Yeah, we don't want to create a new bottleneck just to solve another one.
Exactly. So the eMoE team dug a little deeper and noticed another fascinating pattern, a strong correlation between prompts that come one after the other. You can see this really clearly in figure 9 of the paper.
So if we have a series of requests that are related in some way, we can probably reuse the same set of experts for a while.
Exactly. And I actually tested this out and found that reusing experts for something like 20 to 40 prompts keeps the performance almost the same.
So you're saving a ton of computation without any real loss in accuracy.
It's a brilliant optimization. And that brings us to our next big idea, task-aware expert loading.
Right, we talked earlier about how different tasks have different levels of sensitivity when it comes to picking the absolute best expert. So how does eMoE factor that into its strategy?
Well, this is where it gets really cool. eMoE actually prioritizes the loading of experts based on how sensitive a task is to a routing accuracy.
Meaning if a task absolutely needs the perfect expert match, it gets bumped to the front of the line.
Exactly. While tasks that are less sensitive can wait a bit longer, or maybe even make do with fewer experts altogether.
So it's like a dynamic allocation of expertise, ensuring that the most demanding tasks always have access to the best resources.
And the paper gives a really good example comparing a conversational task, which usually needs very accurate expert routing, to a basic classification task, which is way more forgiving.
All right, so far we've got this expert prediction based on patterns, periodic invocation to minimize overhead, and now task-aware loading. It's like eMoE is running its own miniature AI economy, making sure everyone gets the expertise they need when they need it.
I love that analogy. And of course, no economy runs smoothly without some kind of central planning, right?
Yeah.
That's where eMoE's task-aware request scheduler comes in.
Oh, right, the scheduler. So this is the part of the system that manages the flow of all those incoming requests.
Exactly. Its job is to make sure everything runs as smoothly and efficiently as possible while still meeting those service level objectives, or SLOs, that users set.
So it's juggling a lot of factors, right? Expected token generation length, expert loading latency, and the sensitivity of all the tasks that are waiting in the queue.
It's a tough job, but the scheduler tackles it head on, using what's called a greedy approach. It always picks the task with the most urgent SLO, the one that absolutely needs to be served the fastest. Then it does a quick check to see if scheduling that task would cause any problems for the tasks that are already running.
So it's like a constant balancing act, making sure the most time-sensitive tasks get priority while still managing the overall flow to avoid creating bottlenecks.
You got it. And the details of how this all works are spelled out in Algorithm 1 in the paper.
Awesome. Well, we've covered a lot of ground here. We've talked about those inherent challenges of MoE inference and all the ingenious optimizations that eMoE brings to the table. But I guess the real question is, how does all of this translate into actual performance gains?
That's the million-dollar question. And the good news is the results are incredibly promising. Let's get into those next.
Okay, so we've seen that eMoE has a lot of clever tricks to make MoE inference more efficient. But does it actually work? Like, what kind of real-world performance gains are we talking about?
Well, that's what makes this paper really exciting. The evaluation section is where they put eMoE to the test. They compared it head-to-head with other state-of-the-art inference systems, like VLLM and DeepSpeedFast GN.
And they didn't hold back on the models they tested.
Oh no, they went all out. They used a whole range of MoE models, from OpenMo all the way up to that massive Mixtral 8x22b. And the results, well, they speak for themselves.
Okay, I'm definitely hooked. Let's start with latency, the time it takes to get an answer from the model. How does eMoE stack up against the competition?
Figure 12 in the paper has all the details. eMoE consistently comes out on top, showing up to a 17% reduction in inference latency.
17%, that's a pretty significant speed boost.
And it gets even better. Those gains are actually more pronounced with larger models. So the bigger the model, the more eMoE helps you out.
That's amazing. I mean, that's really where we need it the most, right? Dealing with those huge models. But let's not forget about memory consumption, the real elephant in the room with MoEs. Did eMoE manage to tame that beast?
Oh, absolutely. eMoE delivered some seriously impressive results on the memory front, too. You can see it all laid out in figures 14 and 15. They achieved up to an 80% reduction in memory usage.
80%. That's insane. But can it really achieve that kind of memory saving without sacrificing accuracy?
That's the best part. It manages to keep the accuracy high, just like we'd expect from these large language models.
So we're getting all this memory efficiency without compromising on the quality of the output. That's a game changer. What does that kind of memory saving actually allow us to do?
Well, for one, it opens up a whole new world of possibilities for handling tasks that require a ton of context. With eMoE, you can process prompts that are up to 40 times longer. Think about it, you can feed the model an entire book instead of just a few paragraphs.
It's like giving the model a supersized memory. What other practical benefits does this memory efficiency unlock?
Well, it also means we can now handle much larger batch sizes, which translates to faster processing and higher throughput. They saw up to 4.5 times larger batches and a 1.5 times increase in throughput with eMoE.
More context, faster processing, all without losing accuracy. It sounds too good to be true. But I know there's another big player in the model optimization game, quantization. How does eMoE compare to that?
Right, quantization. It's a popular technique that shrinks those massive model parameters down to a smaller size, effectively reducing the memory footprint.
It's kind of like compressing a file to make it smaller without losing too much data.
Yeah, that's a good analogy. And quantized models can definitely achieve significant memory savings, comparable to what eMoE offers. However, what's interesting is that eMoE actually outperforms quantized models when it comes to accuracy. You can see this clearly in Table 3 of the paper.
So if accuracy is your top priority, eMoE might be the better choice, even though both techniques can significantly reduce memory usage.
Exactly. This paper really highlights the strengths of eMoE as a memory optimization strategy. It's not just about shrinking the model, it's about making those powerful MoE models more usable and more accessible for real-world applications.
Okay, so the evaluation shows eMoE performing really well in controlled settings. But how sensitive is it to real-world variations? Like, what happens if there are errors in task classification or if the parameters change a bit?
That's a great question. And the authors were smart enough to test that too. They looked at how task classification accuracy affects latency. You can see this in Figure 19. Remember, eMoE relies on knowing what kind of task it's dealing with to optimize expert loading.
Right, making sure those tasks that really need the right expert get prioritized.
Exactly. So if the system misclassifies a task, it could lead to some inefficiencies. But what's really interesting is that even with a 20% error rate in task classification, the impact on latency was less than 10%, even for the largest model they tested.
That's pretty impressive. It seems like eMoE can handle a bit of real-world messiness without falling apart.
Absolutely. And of course, we can't forget about the computational overhead of running all these extra components like the expert prediction, the periodic invocation, the task-aware loading.
Right, there's no such thing as a free lunch in computation.
True, but the good news is that the overhead is relatively small compared to the gains you get. They actually break down the time overhead in section 5.7. For OpenMo, it ranged from 0.47% to 1.69% of the average inference time, and for Mixtral, it was a bit higher, but still well under 4%.
So a small price to pay for those huge gains in latency and memory efficiency.
Exactly. Overall, the results paint a very promising picture for eMoE. It's a clever system that solves a real problem for anyone working with large language models, and the evaluations show that it really delivers.
Okay, so eMoE seems like a potential game changer for MoE inference, but what does this all mean for the future of AI in general? As these models keep getting bigger and bigger, what new challenges are we going to face? And how can research like this help us tackle them? Let's explore those big picture questions next. Okay, so we've established that eMoE is pretty amazing in terms of performance. But what does this all mean in the grand scheme of things? Why should our listeners, the people who are really pushing the boundaries of AI, care about this research?
Well, I think eMoE is a glimpse into the future of AI. We're building these massive models, but the hardware we have to run them on isn't keeping up. Optimizations like the ones in eMoE are becoming absolutely crucial.
Right. We can't just keep throwing more and more GPUs at the problem. We need to be smarter about how we use the resources we have. And that's where this idea of task-aware optimization really stands out.
Exactly. It's about understanding that not all tasks are created equal. Some tasks need that absolute top-tier expertise, while others can be handled with a little less precision.
So eMoE is showing us that we can tailor our approach based on the specific needs of each task. But how does that translate into a bigger vision for the future of AI?
Well, imagine a world where AI systems can automatically adjust themselves to optimize performance. They could dynamically change their memory footprint, their expert selection, even their scheduling, all to ensure they're using resources as efficiently as possible.
So it's like having a self-optimizing AI ecosystem. That's a pretty cool idea.
It is, and I think eMoE is a step in that direction. It's a proof of concept that we can move beyond those brute force approaches to AI and start designing systems that are more intelligent, more adaptable.
Now, the paper focuses mainly on inference, the process of using a trained model to make predictions. But what about the training process itself? Could these same insights from eMoE be applied to make training more efficient as well?
That's a great question, and I think it's a really exciting area for future research. Could we use similar prediction techniques to optimize memory usage during training? Could we dynamically adjust the number of experts based on how the model is learning? There's so many possibilities.
And thinking about the task-aware angle, could we even tailor the entire training process to the specific demands of the task? That could lead to some massive gains in efficiency.
Absolutely. Imagine being able to train a model with just the right amount of expertise for the job, instead of always going for the biggest, most complex model. It's like right-sizing your AI from the very beginning.
So there's a whole world of possibilities waiting to be explored in MoE training. Any final thoughts you want to leave our listeners with? Something to inspire them, maybe spark a new research idea?
Here's a thought to chew on. eMoE relies on understanding patterns in expert selection and those task-specific behaviors. But what if we could take it a step further? What if we could predict not just which experts will be needed, but also how much precision each task actually requires from those experts?
It's like having fine-grained control over the level of expertise, dialing it up or down based on the needs of the task.
Exactly. We could potentially achieve even greater memory savings and reduce latency by only activating the level of expertise that's absolutely necessary for each computation. It's about making AI not just powerful, but also incredibly precise and efficient.
That's a really fascinating idea, tailoring the intelligence to the precise demands of the task. Well, that's a perfect note to end on. A huge thank you to our expert for this incredibly insightful deep dive into eMoE.
It was my pleasure. Always a great time exploring cutting-edge research with you.
And to all of you listening out there, keep pushing the boundaries of what's possible with AI. We'll be back soon with another deep dive into the world of groundbreaking research. Until then, happy experimenting.